Okay, welcome back to my lectures. I hope you have digested Valentin's lecture of last night. It was hard and large. Benoit, he told me to be simple, to make things easy. My slides have another profile than Valentin's. We complement each other and we work very well together. As I told you yesterday, this was my title I got for my first lecture, and I decided to just continue there today because I didn't manage to finish. So it was about nonlinear optics and their application with lasers, and also a bit about parametric devices, how we can engineer them for various applications. So yesterday we were on the parametric devices. So now I will give first some examples and then see how we can tailor nonlinear materials a little bit more. So I started off my lecture with some examples, and one was this remote sensing. So you have some biological particles that are approaching you, and you want to save the people's lives here. And therefore you shine with the laser and you will try to identify what is approaching you. Is it just the ordinary cloud over the Mont Blanc, or is it something much more difficult? And this has, of course, a lot of both military and civilian needs. And we were looking mostly on the biological side of this. And then one should go to the ultraviolet and look at the spectroscopic response of the possible proteins and amino acids. And one very characteristic is tryptophan, but also tyrosine and NADH. And if we look at the absorption and emission spectra on this, so we are going to look remote, so we have to have a LIDAR system and collect the fluorescence. So we collect this and maybe we excite here. And then for tryptophan, this 280 is very nice. And okay, so we are going to shoot over long distance. So the atmosphere has to be transparent as well. So you have to go down here in this wavelength region. And at 340, there is a similar characteristic wavelength range. And you would need at least 2 wavelengths to be able to get some kind of character of these molecules. So we were in this project with the Swedish Defense Agency, and then we proposed to use, as also Valentin and others have talked about, simple JAG lasers to be able to build a compact system that you can transport easily. And then a OPO, and in the OPO, then we are doing a mixing here in a UV crystal, which is BBO. So in this very compact setup, then we immediately, so we start with the green and we generate red. And from the red, we mix it some frequency with the green, and then we can get this UV. And luckily then, we can get both of these characteristic wavelengths at the same time. And we get tunability on the same time as that. And by changing the grating of the nonlinear crystal, which in this case was PPKTP, which operates easy in the visible at high intensities, then we can get all of this wavelength here. And you can see how compact this system was. And then the next problem is, of course, to collect all the information, and then you have to call in the spectroscopist. And it was then a matter of measuring on many different species and under real conditions also. So they want to be able to measure up to several kilometers of distance, say 2 kilometers. And one interesting finding was that when, depending on the surrounding, for example, some spores and bacteria, if they are connected to water, they have a certain spectra. And when they are dry, they have another spectra. So it's really a multi-dimensional system. So you have to call in your computer guys to try to identify the molecule. And in fact, at this point, they only can identify the class of molecules or proteins that are out there. But still, it's supposed to be useful. So with a little bit of knowledge in nonlinear optics, then you can build such a system. And this was just designed by more or less by one PhD student. Okay, as you saw yesterday, it's of interest to go also, of course, to longer wavelength. But we also learned that it's quite difficult. The materials are difficult, etc. And now it's the very hot topic to go to the terahertz gap, and I will show you slightly in a few minutes some ideas we have to reach here. And then it's more about how we build a laser, and then combine it with some quasi-phase matching material. And of course, again, medical imaging and sensing is particularly interesting here. Okay, so leave these applications for a while, and now I'm going to talk about if we structure in 2 dimensions. So we call that nonlinear photonic crystals. And what does it mean? Well, it just means that we have one more degree of freedom. So we can generate many wavelengths. If we have a broad spectrum coming into this crystal, we can generate many wavelengths as seen here at the same time. So we have many phase matching processes ongoing. And these have some advantages and some disadvantages. For example, to understand what you're doing when you put the crystal in front of the beam. So you get quite broad bandwidth here, and these are then non-collinear here, so you have a bit of a lower efficiency. So it's just to add here, so here is the phase matching condition, and to add a second term here corresponding then to if we look in the reciprocal lattice, to additional coordinates here. And then as we are primarily experimentalists, so we do that. So we take our KTP crystal and we pattern that, and this is quite an old experiment, pattern it in 2 dimensions with a reasonably small period, which we can do in KTP. And then if we look then at the possible grating vectors, then there are many possible wavelengths that we can phase match if we launch a beam into such a sample. And they will then, of course, go out from forward direction and out in different directions. So here is the angle versus the wavelength. And now it's just either to take a very broadband source or a tunable laser. And we took a tunable laser to demonstrate this, and probably, I don't know if you can see these weaker and weaker beams coming at different angles. So of course, it's a symmetric process, so you get equally much to the left and the right, so to say. So there was just a proof of principle. It can also be done for a parametric process, and then it gets a bit more complex. And here are example done in lithium tantalate instead. So we have then these grating vectors, and they can generate many different wavelengths here, parametric, due to the broad parametric fluorescence. So it's a matter of making a nice polling and then to do the experiments. So here are the processes we are going to look at. We are going to look at signal and idler for these 2 directions. And here is the sample that we then, well, it has a longer period here, and we launch a more intense laser here. So this is now a picosecond Ti-sapphire laser. The previous example was just a continuous way. And then when we rotate the sample a little bit, then we get an asymmetric case, and we can then isolate the 2 combinations here. So we have, for example, one case which we found particularly interesting. Then for these 2 grating vectors, we have a common idler. So the idler is going in the same direction, and then we have 2 different signals corresponding to the 2 grating vectors here. So then one can think that they communicate over this idler here. So we have a coherent exchange, and this is, of course, interesting for those working in quantum optics, and perhaps Katarina knows all about this. Here is the experiment. So this is the picosecond Ti-sapphire laser, and then we collect spatially separated signal and idler here. In principle, only the signal. So we'll launch 800 nanometer, and this is the spectrum we get out of the phase matching curve. So here's the thickness here corresponds to the bandwidth, and here is a typical spectrum then. And that's for one of the cases, and this is for the other one. So you see that they are exactly, or more or less, as good as we can do it experimentally, the same. Okay, and then to be able to check this coupling over the common idler, then one has to do this with a few photons instead. And I think we will see good results on that in the future here. Another thing we can do is to go to very small gratings. So this has nano-gratings in KTP. I told you yesterday that we can make very small domains, and we can propagate them very deeply. And this is a technology that my colleague Carlotta Canalias has developed. And these are some examples of crystals that has been selectively etched after periodic polling. And they have a period of 700 nanometers. So each domain is like 350 nanometers. And these pictures are quite old by now, but she does a bit smaller than this. So this is from the top face, and this is from the bottom face of something that is 1 millimeter thick. So to get some perspective, there is essentially no broadening from the top to the bottom. It's like having a domain which is 1 meter wide, and it's 3 kilometers high, and then it's 10 kilometers long, and you put 10,000 of them after each other. This is the kind of material problem that you have to face to make them. And if you put too much field when you pull them, then there will be only one domain here. And she used some processing tricks to get this. Okay, if you have such a device, what can you do with it? The first one we showed was that you can actually have see this as a Bragg reflector. So if we, after it's pulled, and it has domains up and down, and if we apply a field over this one, not a polling field, but a lower field, then these domains will acquire positive and negative refractive index. So we have a Bragg stack here. So if we shine a broad spectrum onto this crystal, it will reflect certain wavelengths. And then we demonstrated that with a tunable laser, we can hit these Bragg peaks. And here it was still a higher order Bragg reflection for the Ti-sapphire laser. But at 1.5 microns, I think one can reach today with the technology available, maybe first order. And if you do it in a waveguide configuration, it can be quite a low field required to do this. And then it could be interesting, for example, in a telecommunications WDM system if you want to tap off a signal, because this is an electro-optic effect, so it's more or less instantaneous. So you can think of applications here, other applications in telecom. Okay, if you shrink the domains, it makes that this delta K that represent the quasi-phase matching, it becomes longer and longer. So in normal devices, we have periods maybe 5 to 20 microns. If we now go to 0.5 microns or so, then it means that the delta K becomes 10 times longer. If we look at the phase matching diagram, it means that we can actually put, for example, the second harmonic going backwards. So we can start to generate light in the backward direction. And this is also what we demonstrated, backward second harmonic generation. And also later I talk about parametric generation. And this is some kind of example of how this is. So this is the weak backward generated, and this is some residual forward generated that is not intended to be generated, which is still stronger than that one. But if one do those experiments again with the state-of-the-art devices that we have, I think one can get quite a substantial backward generation. So this was more proof that you can do a completely new type of nonlinear devices that doesn't exist with, for example, birefringent phase matching. It has also been proposed a long time ago by Steve Harris that you can, the same way, make parametric devices. And then, for example, you can send the idler or the signal in the backward direction here. So if we pump such a crystal, here is the pump grating vector. Here is the idler going backward. Here is the signal going forward. And here is the grating vector. So here is how this match in this particular case. Then the signal will grow like this. The idler will grow like that when you pump this one. And we call this for mirrorless optical parametric oscillator, because then you don't need any mirrors here. So it has some resemblance with for example, Bragg lasers, but not exactly. So here is here's an animation how the waves may propagate in such a case. But here is the phase matching diagram then. So if we see what we can generate at the moment, so we are somewhere here in the QPM period. It means that the idler will have to go backwards. And the signal and the pump, of course, in forward direction. If we can shrink the dimensions further, then we can instead send the signal in the backward direction. So then we need to come down to, and these are with reasonable available wavelengths up to maybe 1.5 microns. If we want to send both the signal and idler backward, then we need to go down here. So this is going to be quite tough, at least if we use our thick crystals. And here is an experimental setup for this. So here is the crystal. We pump it again with picosecond pulses to get a high intensity here. And essentially a pulse which is long enough to fill the whole crystal at one time, because it's one pulse, and during that pulse we are going to generate a parametric light in the backward direction and the signal in the forward direction. And here is a diagram how that goes with the pump intensity. And we can get decent efficiency here, so something like 16–17% efficiency. Then the signal, okay, we pump at 820, signal is at 1100, and the idler is at almost 3 microns. And this was also a project with Carlotta pushed. So I'm not a co-author of this paper because I thought this is, of course, nice, but where's the practical realization? But this is, of course, important to see that young people, they drive their own ideas and they want to do it because they want to do it. And old farts, they are ignorant. Like my colleague at the Nano department said that, and why did you publish this in Nature? I don't understand. Why didn't you just put a mirror here behind, and then the beam would have gone in the backward direction? So this is how professors get. A key point here is the high nonlinearity that Carlotta got out of this device. So this is very close to what you get for forward ordinary grating, so to say. So there is a lot of work behind this. Some of the interesting features that has been analyzed is the spectral properties here. So here is, for example, what happens when you tune the pump. Then you can see that the idler stays constant in wavelength, more or less. So it doesn't change at all. Sorry, here. There's very little change of the idler, while the signal takes all the change when we change the pump wavelength. So it goes 1 to 1 there. And also spectrally. So we couldn't really measure the spectrum very well there, only that it's smaller than, so it's very narrow, smaller than our spectrometer. And all the bandwidth is taken then, so the bandwidth of the pump is converted to the signal. So it's more or less a matter of the quality of the grating, the bandwidth here going backward. Okay, what else can you do with these devices? Here is something that we did. We knew that one can also use this off phase matching, so to say, and then you can use them for mode locking. So get an enhanced cascaded Chi2 process. So if we put such a PPKTP for frequency doubling here in the cavity of a yttrium vanadate laser, and we operate this one off the phase matching and put the intensity right in that, it means that in the forward direction we generate visible, and then in the backward we convert it back with a phase shift. This annoys the laser so that it starts to self-mode lock. So we generate 2.8 picosecond pulses here, and here is a collected screen of all these pulses. So that was quite nice. With the cascaded Chi2, you get a much better Chi3 than in ordinary materials. And in fact, if we now also put some electrodes here, so to help this switch on or switch off, and we put a gate here, so using a Carl-Lenz mode locking scheme here, then we can switch on and switch off the mode locking this way. And because of the amount of slides I have, I will not go into the details, but essentially you can switch on and switch off the mode locking. Okay. Yesterday, we heard a lot about how we can go to longer wavelength, and this is by this orientation pattern, gallium arsenide or gallium phosphide. Here in France, Thales is growing these crystals, and they are quite getting better and better. And it's nice to hear that one can maybe even get some samples once in a while. Some example. You saw many examples yesterday, but here are a few examples that I picked, and they are primarily some slides that I got from some of the students at Stanford University. So OPG, you can see how you can cover a very broad bandwidth here. And then if you want to do spectroscopy, cut out those pieces. And you saw also in my previous slide how you can slice a piece and take it to a second sample and amplify that. And here are some examples of what you can use this for. So SHG maybe not so interesting unless, of course you can design it for CO2 laser. Difference frequency generation, OPOs, and then terahertz is maybe very hot. And at the very end I will come back to that. If you want to go in the opposite direction, we don't have any good material that we can grow or have been able to grow the same way, and no ferroelectrics that we can pull, at least to very short wavelengths. There is now some material coming out from one of our previous PhD student, Junji Hirohashi. But a general feature for these UV materials is that they have very low nonlinearity. Suna Kurimura, he has developed another technique where he is more or less press-inducing structural change in quartz, and then he can use that to do UV generation. And of course, one interest for this is to make shorter and shorter wavelength sources for lithography, but maybe the technology for making shorter line width is running away, because before they wanted to do 193 nanometer, but now they're going to even shorter wavelengths for the electronics. So this is, of course, if somebody could get ferroelectrics that can have UV transparency, it could be very important. So maybe this was the last of yesterday's talk. So I think nonlinear optics complement lasers in all kinds of photonics applications. And a lot of the technology is already mature. So you can buy these samples from various places. And guys like you invent new concepts and devices. And applications are, for example, that I know a lot in biotechnology. And then I haven't not been talking about quantum optics because there has been so many sessions on quantum optics here already. And then, of course, displays, particularly for making the green laser, it's important to have these devices. And then it's just to go out and buy them. So maybe I stop here for this part, and then I have a second presentation. And you can ask questions here now if you want, or otherwise I just load my second presentation. Okay, mon frère Benoit, he gave me a second topic, lasers for nonlinear optics, and I'm so ignorant, so I just take them one by one, and then I don't think about it till it's time to go here. And then I have to sit after Valentin's lecture, and I work half of the night. Okay, so lasers. And now we're going to start up basic, and then maybe see how optical engineering can work. So here is an outline of this talk. I will start with diode lasers because they are so neat and cheap. And this is, I mean, when I started my own research, I had no money. So the only thing I could do was to buy small stuff. And also, I can also only understand small stuff. And then you have to listen to other people and see what you can learn from them. And how you can stabilize them and tailor them for your things. And then, of course, he said that I should do solid-state lasers and fiber lasers. So we have done quite a bit of work with fiber lasers. And then in combination with volume Bragg ratings, which not so many other people have done. And some examples, and maybe some terahertz at the very end. Okay, simple. Types of diode lasers. Edge emitters are the first one that was available, and they are then often very inexpensive, and these are good for a lot of things. Array lasers are not used so much in nonlinear optics, more for pumping of solid-state lasers. The same with broad area diodes, and here it's of course a spatial problem. But it's worth mentioning that this kind of laser was used by Matsushita for their laser TV. So they put a lithium niobate waveguide behind here. And then all the time, and this laser is changing the mode pattern. It means that the second harmonic is changing also all the time on the output. And it's not only spatially, but also spectrally. This means that they lose all the coherence, and coherence is one of the big problems in laser projectors. So you have to kill coherence. So this is something they got for free, and so that's what they have in their laser TV, if you take it apart. And then I mentioned also this taper diode, which is essentially a way of taking this diode and then amplify it, so with a flared amplifier. And then there is a lot of engineering to get a nice beam profile out here. So often in the intensity distribution it looks like this, and we are used more to Gaussian beams, so you have to do some beam shaping here, or just lose light. And then the final type that I mentioned also yesterday are these optically pumped semiconductor laser, or VCSELs. So you pump them from the side, and then the cavity is here. And they have very high intensity inside, and a very high reflector normally here. And then you can, in various ways, integrate your nonlinear component in that cavity. And these are what Coherent are selling when you buy the visible lasers, and they can have output powers up to watts. And you can also combine them with carbon nanotubes and things like that, and mode lock them, and etc. Okay, so now you know about lasers. The main problem with diode lasers is maybe their spectral problems. So they are sensitive to feedback, and they jump around, and when you change the temperature, they change the spectrum maybe over 10, 15 nanometers. So you have to lock the wavelength, and you can do it with a conventional diffraction grating, but it's rather bulky. So instead, it's better to use maybe fiber Bragg gratings that you can more or less glue on the chip here, and you can buy these units here with the integrated grating, so they are quite wavelength stable. And for example, at 980 nanometers, these are commercial, because that's how you pump the fiber network, the erbium amplifiers. And then it's also important that they are stable over time. Okay, here it was also the grating integrated. These are still expensive, these lasers. But the volume Bragg grating, you can also put it behind such a flat amplifier and then form a laser. So you use the output here more or less as the laser mirror, and this as the back mirror. And then we maybe like to do some tuning, for example, for spectroscopy, or to hit the wavelength of the phase matching. So you can end up with the case that you have a laser at this wavelength, and half a nanometer away, your QPM crystal has a narrow bandwidth. So you really need to get one of them to overlap with the other. And then if you have a fiber Bragg grating, then you can just stretch the grating or compress it. Then you get a bit of tuning. Or if you use the volume Bragg grating, use these chirp gratings that I showed. You can also, in fact, sometimes put several gratings into fiber or a VBG, and you can get several wavelengths then. And I will come back to the possibility of tuning by putting the conventional VBG in a retroreflector. And then now when we work with the diode lasers, they have low output power, and some of the crystals have low nonlinearities, particularly seems like those that are very robust to power, they have low nonlinearities. Then you have to build various kind of cavities to enhance the power. But of course, resonant cavities already put a lot of additional on your laser requirements. So you need locking techniques, and they can be successful or less successful. Okay, so that was the simplest laser. Then maybe the laser giving more power is the diode pumped solid state laser. So here we have a laser medium, a crystal normally doped with a rare earth. And this rare earth, they have narrow line width normally. And most important maybe that they give a high quality beam, and we store the energy. So if we look at the energy diagram, we pump them up to the upper level, and then they relax to the laser transition, and then they lace down to the ground state or over the ground state. And there is a quantum defect, we call it, the heat generated in the crystal. And this one, if we want to scale power here, we have to make as little heat as possible in the laser medium to avoid distortion of the beam. Okay, so if you go to Hamburg, you know all about this rare earth and where all the transitions are, and you can look at this, and people have laced more than 10,000 of these transitions. So the important thing is that the electron shells, they are shielded here. So the atoms are like isolated atoms like in a gas. And we have a different host that we can use. YAG is, of course, very convenient. Yttrium vanadate gives you polarized emission, and if you want to build a big laser, maybe you use the glass. We have worked quite a lot with the double tungstens and also together with Valentin here. So you can get high doping in these guys. So you can therefore use shorter crystals, and they are quite suitable for diode pumping. Which of these are more important? Maybe neodymium, ytterbium, erbium, and thulium, holmium. It's those that have been mostly exploited. And here, I showed you this picture yesterday, and here you can see the energy diagram, how you can pump it, for example, at 8 nanometer, and then lace the different lines here. So this one gives the blue, this one gives the green, and here gives the red. So when you buy green lasers, they are almost always done with this transition here of neodymium. And I also mentioned that we can package them quite effectively. So we are talking about small crystals to make micro lasers. And here is a wafer of yttrium vanadate, and we can cut it up in such small pieces. Then, okay, before you do that, you coat these crystals. And then you can integrate it on, for example, on a silicon chip. And this is technology that was first used for fiber bundles for telecom industry. So here are the diodes, and then the V grooves are etched into the silicon, and the fibers are positioned with micrometer resolution or precision. You can also integrate the Q switch here. So this is one of these chips here. This is a pure, I think this was the yttrium vanadate chip. And here is a JAG chip integrated with a passive Q switch, a chromium YAG. And such a small laser then, which is just a few millimeters long, can give very intense pulses for marking. And you can take it to a fiber amplifier and amplify it in quite a neat way. And I think similar concepts are commercially available. And we also looked at possible ways of making this even simpler by making a mold in a plastic. So here is a copper-based polymer, which is quite good heat conduction. And then one can think of mass fabrication of these lasers. So they get really cheap. And then you think about those green pointers, how inexpensive they are. Other possible variations is, for example, to use erbium. And erbium emits at 1.5 micron, which is considered eye safe because it doesn't penetrate into the retina because of water absorption. And if you bond on a Q switch here, which is a cobalt spinel, it's called, then you get kilowatt pulses with a 1 watt pump diode here, and reasonably short pulses. And with an etalon in the cavity, or the Q switch as an etalon, and tilting that, you can also get a tunable device for spectroscopy, which we have exploited. And this kind of laser then can be taken on to nonlinear experiments, as I will show you. And here is another variation of this laser. Here is again the erbium ytterbium. It has an output coupler, and then we couple it through the optical fiber. And I said that we can stretch and compress the optical fiber with a piezo in a ferrule. And then we get a laser which is tunable over 30 nanometer with extremely narrow line width. And then you can do gas sensing with this one, or you can combine it with other lasers to go to the mid-infrared. And the whole idea here is that you make compact, simple lasers that are reliable and to get the overall system to be efficient. Okay, and another component then was the volume Bragg rating, and I mentioned that this is written into the glass with a UV laser, and then you do a heat treatment and you get a permanent grating there, which is really robust. And you can set the spectral bandwidth and the reflectivity according to these simple interference rules. And then why should you use them for example, for solid-state lasers or lasers in general? Well, you can reduce the line width and you can stabilize it. We will get the tunability. And you also get some spectral mode filtering here. And I'll see if I can get into that also. And you can get very low quantum defect lasers. So you don't have to lace here at the peak of the emission, but you can lace very close to where you are pumping, as I will show you. The glasses that are available today, they go from 350 to almost 3 microns. They have a very high damage threshold, low absorption, and low scattering, so that's important. However, when we scale up, this absorption is still sometimes a problem. Okay, so some of the applications. Maybe I skipped that one. So where have they been used? First, they were used for stabilization of diode lasers. And then we put them in diode pump solid-state lasers and OPOs. In fact, first in the OPOs, as I showed you yesterday, and then in other diode pump solid-state lasers. You can also use them as beam combiners. And in the US, they do this for military applications. So they combine several lasers here, and they use the VBG as a reflector. So they will reflect a certain wavelength, and for all the other wavelengths, they are transparent. So they can just do a beam combination here. And you can think of lasers with hundreds of watts or 1,001 kilowatt, and then you combine them to dangerous things. If you put the chirp in here, you can, of course, use them as a grating for pulse compression, or you can use them as filters, which is also commonly used for particularly Raman and biology applications. And you can reduce amplified spontaneous emission by filtering out your signal here and forget about the rest. So here is one of the first lasers of this kind that we built. And then we put the VBG in external cavity. And then, so we have a dual cavity. Here is the first cavity, and here is the second cavity. And then so this guy put the lasing wavelength. Here is the main gain of the erbium at 1535 in this glass. And here was the reflectivity of the VBG. So the laser is going here. And here's an energy diagram, maybe not so interesting. Okay, then we had a piezo on this guy, so we can do fine-tuning. And it's running with a very narrow line with 90 kilohertz. And this is how much we could tune it in this case with a piezo. Okay, after that we built various lasers where we just more or less glued VBG on the chip here. And in that case you get the stable cavity because there is some heating of the laser medium, and this bulged the face here, and then you get stable modes. So even if this guy is like a flat mirror. And one of the neat things then that you can get really low quantum defect lasers, and I think the lowest quantum defect lasers has been published this way or built this way. So you can pump through the VBG here, and the VBG doesn't distort the pump. You don't need an isolator or anything. And then you have the cavity here between this mirror and that mirror. And you can, so here is an example then of the lasing wavelength, and here is the pump light. So they are very close. There is a quantum defect of 1.7% or something like that. So this is one of the shorter wavelengths laced for ytterbium. And you get this very narrow spectrum here, which is important in many cases, particularly for nonlinear optics then. So 10 gigahertz. And otherwise it's much, much wider. Okay, and the tuning. So we get beam steering, of course, if we rotate our VBG, but if we put it in a retroreflector here, and this is the pivot point, then the beam is always coming out like that, and we can put the mirror here. So you see. And then, of course, the effective grating pitch is going like that with the refractive index and angle of the incidence. So here are an example of one such laser where we utilized ytterbium and very simple laser. Just rotate it here. It gives a few watts of output power, tunable from below 1 micron to 1045. And this is then a laser which is complementary to the Ti-Sapphire laser, which is dropping off here. And with another VBG with slightly longer pitch, we could instead work in this region. Okay, nothing more to say. Well, here is something about the reflectivity. I have also some slides at the very end where we can talk about some mode filtering, etc. But with respect to time and your tiredness, I skip it for now. If we want to go to high power, then of course this low quantum defect is important because of the thermal problems otherwise induced. Simple first approach is just to pump more and more, and then your laser doesn't work. So you have to take care of thermal management, and thin disk laser is one such. So you have a very thin laser crystal that you cool strongly from the backside. So then, of course, you say you have a very small laser medium here, and not much energy can be extracted. But you have to recirculate the pump here, back and forth, back and forth, back and forth, and then you do absorb a sufficient amount of energy. And this is a concept primarily developed in Germany. And then fiber lasers is the competing technology where you have a long fiber length, which has a large area to volume ratio, and therefore you can efficiently cool it. So we have worked not on the thin disk, but on the fiber lasers. And of course, you have automatic mode filtering when you have a mode guided in the fiber. So primarily a single mode. And the pump light can be launched in the cladding, so-called double-clad fibers. So it's easy to get a lot of energy in here, and it takes some time before they have all been absorbed in, or most of it has been absorbed in the core. And then we can cool it. And they have, this is in a glass then, so we have a broad emission spectrum. So they can be used for ultra-short pulses, or we can do tunable devices. And I mentioned already fiber Bragg gratings, which can be written directly into the fiber. You can also use external gratings, conventional diffraction gratings, and believe it or not, we can use volume Bragg gratings. Here we used a special neodymium fiber developed in Stockholm. So it has a central core here, and we could pump it in this region here. This is with a conventional mirror, the spectrum, and here is the VBG spectrum. And the efficiency is more or less the same. In some cases, we even get a higher efficiency with the VBG, but it's on the percentage level. And then tuning, of course, if we utilize this pivot principle, then it's easy to tune it. And I took some example where you can get tuning here. It looks a bit broad here, but it was our spectrometer which shows that. So you get about 30 nanometers of tuning directly this way. And the line width is 5 gigahertz. This was an ytterbium laser also. Okay, so the next thing we thought that we need to learn to do high power lasers. So we started to collaborate with Andy Clarkson in Southampton, and then we took first the erbium-ytterbium laser, and it has to be pumped quite hard. So pump it from the two sides. We used the cleaved end phase on one side and the VBG on the other side. So we had the output coming here, and to avoid any problem with the ytterbium, we let the 1 micron light out there. And then this laser gave more than 100 watts of output power. And here is the spectrum with the VBG, so in a narrow line, 0.4 nanometers. This is with the conventional diffraction grating, so edge grating. And this is free running. In the roll-off, you can see here, that was amplified spontaneous emission. Okay, maybe worth that this fiber, which was from Southampton, didn't have the perfect beam quality, actually, but still maintains a narrow line width, but of course not single mode. Okay, and then we did also the tuning. And then we did ytterbium fibers, and it's much easier because of the high gain here. VBG on one end, and then just one pump source. And we have a slope efficiency of 75% and no roll-off of this laser. The same dimensions essentially on the core here, so it's not best beam quality. And then we decided to build in-house this, and to do, I got a German student, so he's very serious about all the modeling and everything. And managed to get a really, really nice laser here. And the reason why we built this was as a tool for studies of nonlinear optical materials. So because people asking us, you pull these crystals, what are they good for? Should we use lithium niobate? Should we use lithium tantalate, KTP? And then I could always answer something, but it's better to know. So we developed this fiber laser here. So it is a single mode, transversely single mode laser, very good beam quality. It's polarization maintaining thanks to this thin polarizer. It has a chirped VBG, so it's tunable. What else? Well, it's tunable from 1064 to 1073. So we can simulate YAG lasers. Here is the spectrum in dB scale here. So it's the noise floor is 55 dB below. The bandwidth is 50 picometers, and the temporal stability is very good. And then one can even think about how much more can you squeeze out power here, because you don't see any roll-off. And then if you look at the nonlinear effects, SPS threshold, for example, should be up in the kilowatt regime. So with more pump power, it could certainly be possible to squeeze out more power. But in fact, the nonlinear crystals could not at all take this power. So here is a first example of that. What should I say about this? Here we try to make green light, okay. And we test one of our crystals, and this is a rubidium doped PPKTP, which is maybe the latest material that we work with. It's a bit easier to pull because of the rubidium in the crystal. So it's less conductive, so Carlotta can make nicer crystals there. Okay, here we see some kind of launch power. Then we should expect in the beginning a quadratic rise here, but suddenly it starts to be linear. And we get only to 8 watts of power here for green light for 30 watts of input. And here's the efficiency, 25% the conversion efficiency. It's still a nice beam, but Peter, he stopped here and said that this crystal is crap. And then we looked at some other crystals. So the one which is better here is KTA. It has this is based on linear absorption. KTA can go to almost 15 watts before we see the same features. But you know, we had 100 watts to work with here, so we don't use our laser at all. Then we have been looking at ways of compensating for these thermal effects, changing the focus, cooling effects, chirp gratings, etc. And this is kind of a work under progress. A lot of thermal simulations has been done also on this. And Peter is writing up his thesis together with Staffan Schönhammer, and they are working this together. Then we were looking into the possibility of OPOs instead, so maybe OPOs is better. Then we took our PPKTP here and made CW OPOs. And they didn't work very well, in fact. Normally in pulse regime, PPKTP OPOs work very well. So we changed to magnesium doped lithium niobate. and here we put in a VBG with a variable, one fixed grating, but a variable reflectivity. And the variable reflectivity is because when you pump the OPO, so I think we learned yesterday that you need often more than 1 watt to start the OPO. And here you can see for different reflectivities how the OPO behaves. So we get up to efficiency of about 75%. Altogether, we could get out 30 watt CW from this OPO. And the nice feature was that it's running single frequency. It's always running single frequency. And the signal is at 1.5 and the idler at 3.4 micron, I think. This is then a tool for various spectroscopic applications. And now, okay, then we also built this one with the chirp grating, and then we could get nice tuning, but not at the same power level, really. But the point here is that depending on how much pump light you have, you can choose the reflectivity of the VBG to transmit the right amount of light and leave the rest in the cavity. So run it something like 2.5 times over threshold, which is the optimal. And here are just the graphs of the grating position and the reflectivity. And lately then Peter rebuilt this laser because we had a visitor from Taiwan, Jianqi Huang, and he works on the terahertz then. So he needs 2 wavelengths that we can tune relative to each other of high power and high spectral purity, and then mix them in some nonlinear crystal, for example, gallium phosphide, to generate the terahertz. So he wants to have something like a milliwatt of tunable terahertz radiation around 1 micron, or between half a terahertz and 2 terahertz. So this fiber here, I said it was polarization maintaining. You can lace it at the 2 polarizations. So you can lock 1 wavelength for 1 polarization with 1 VBG and the other one with the other VBG. And then if you match the reflectivities the right way, then you can get the 2 wavelengths to have the same power and get it to be done quite stably. And then tuning relative to each other. And here are examples when they are far apart, and here is where they are close together. And the scale here is maybe important. So it's again down by approximately 50 dB. And the total power we extracted was close to 80 watts. And very low power fluctuations, and then the difference between these two. So now the next experiment is to do this terahertz generation here. So I think I'm reaching the kind of conclusions. I have also something about damage, but maybe we talk a little bit about what you can do with lasers and nonlinear optics instead. So we tailor the lasers. If we cannot tailor the nonlinear materials, we have to tailor the laser to get the functionality we want. And of course, for the process we are after. And I would say that volume Bragg ratings are very useful because they are simple, cheap tools. You get line width, a spectral that you want, often a reduced line width, stable operation, tunability, good beam quality, sometimes even improved efficiency, and low quantum defect can be good if you want to scale power. There has been so many people involved in this work, so I don't list them all, so I call them friends. I would like to acknowledge the Swedish Science Council and a center which Gert Leusch is supporting. My partners doing fibers at Acreo. And if you want to find the references, they are at our homepage, but I did not put many of them on the papers, on the slides here. I think I stop here for now. Maybe better short than long, right?